So indeed, I'm working on direct imaging at high contrast and high angular resolution. And I'm going to present us some of the processing methods we developed in order to image the circumstellar environment. So let's go. So let's start with a short context. So direct imaging, in fact, is very simple in its principle because it consists in directly observing a young star with a dedicated instrument in order to detect exoplanets and to image the structure of the material, of the gas and of dust in the close environment of young stars, because exoplanets can form, for instance, by accretion effect of the material. So the key scientific questions related to these techniques are related to the frequency and to the diversity of the planets. And you have here the famous population diagram of exoplanets as a function of their mass and of their distance to the star. And the population in purple represents the population of gas giant planets uniquely probed thanks to direct imaging. Other questions concern the diversity of the system, the formation and evolution process involved in the formation of the planets, and also their interaction with the circumstellar material, because they can form inside this material. And you have here an example of reconstruction from high contrast data from the SPHERE instrument, in which you have here a kind of a kick, a structure that can be reproduced by hydrodynamical simulations and explained by the presence of a perturber of an exoplanet in formation inside. Okay, so to tackle these goals, direct imaging requires to collect a large number of photons to reach a high angular resolution and a high contrast. So we use the data from dedicated instruments such as SPHERE, but there are several ones we are working on also. At the VLT, which is equipped with adaptive optics and coronagraphy to block most of the starlight on the optical axis. But in spite of this cutting-edge facility, the unmixing task, by unmixing I mean the signal of the object of interest on the one hand, exoplanets and the circumstellar material, and on the other hand, the noise. We need to perform this unmixing to leverage some dedicating processing algorithms, and this is what I will try to illustrate in this rest of this presentation. And to emphasize this need, I'm showing you here a typical sequence of data recorded by a high contrast instrument. Here, this is SPHERE and the VLT, so this is a time series. The star is at the center, blocked by the coronagraph, and you have in the red circles zooms on the exoplanet, and on the right some slice cuts along the black straight and dashed lines. So here you have some examples of data we have. So it's clear from this example that the signals of the object of interest is very faint because it is dominated by what I'm calling in this presentation the nuisance component, that is to say the sum of stochastic noise plus of speckles also, due to residual aberrations in the presence of diffractions. And this nuisance is very strong. Non-stationary, which means its properties varies according to the field, to the position in the field of view, multi-correlated, both spatially and spectrally, for instance. It also displays some strong fluctuations, such as here near the star, because the centering behind the coronographic mask is tricky and not perfectly stable across time. And well, the mixing task is tricky. And to perform this mixing, we will leverage different and complementary signal diversities introduced by the observing strategies. So there are several kinds of diversities, and here I'm focusing on two we are exploiting. The first one, this is a temporal diversity. We have several images, and across the temporal axis, the nuisance component is almost the same. We said it is quasi-static, up to fluctuations that should be modeled very accurately to remove this nuisance component. And for the object of interest, for instance, exoplanets, they describe across time an apparent motion, which is completely predictable because this is an induced motion during an apparent motion, if you want, due to the Earth rotation. So this is completely predictable, so we can leverage this prior knowledge for solving the unmixing task. Second, complementary diversity. We have the same kind of data, but at multiple wavelengths. or multispectral data. And here the behavior of the signal is reversed. Along the temporal axis, of course, planets are static, the same location, spectral axis, the planets are the same location. And concerning the nuisance, describe kind of motion, if you want. This is the same template, the same shape of the speckles, but magnified by a factor, like an homothétie, proportional to the wavelength according to the laws of diffraction. So here also we have a prior knowledge that we can leverage to solve the unmixing task. Okay, so I will present here two approaches to leverage these diversities and this kind of data. The first one is based on residual learning. In fact, by residual learning, I mean that we will leverage a statistical model of the nuisance to capture most of it, to remove it, and after that we will train a more flexible, we will use a more flexible or more complex model to capture the residuals, that is to say, to capture the discrepancy between the statistical model and the reality of the observations. So for the pre-processing part with the statistical model, this is quite simply. We model the nuisance by a multivariate Gaussian law, which means that we are estimating the mean fluctuation along the time series, removing it from the data, we're centering the data, capturing correlations both spatially and spectrally, to capture the structures of the nuisance, because we saw in the introduction that it is very correlated. We whiten the data, we end up with this kind of residuals, and we use these byproducts to train a neural network to solve a pixel-wise classification task. And we do that in a supervised fashion because, in fact, the object model is well known in this case. The signature of an exoplanet, this is just a blob. This is it takes the form of the of axis PSF. The direct model is known, so we can leverage it to generate synthetic planets into real data to have our training samples. We have a loss leading with class imbalances, and we have also a specific data augmentation strategy, because here the training is dataset dependent, which means that when we have another data cube, we retrain the model in this specific case, because the observations are very different from one night to the other. And once the detection is performed, we perform a regression task with another network, minimizing the mean square error to estimate the flux of the planet on small patches centered on detected planets. Okay, so let's move on to some results in the form, so this is detection results in the form of detection contrast curves, which represent on the y-axis the minimum flux that an exoplanet can have to be detected at a given and fixed probability of false alarms at a function of the distance to the star. So the lower is the better, and the curves are decreasing because, of course, this is harder to detect planets close to the star than far away. The proposed approach with the mixed model is in green. Here you have a statistical model in orange of the nuisance component without deep learning and implementing batching filtering for the detection. And in red, this is a baseline implementing principal component analysis in order to build a low-rank model of the quasi-static speckle. So it serves as a baseline. So the interesting point is that, of course, we are improving the result, but the interesting point is that far from the star, we are reaching the ultimate detection limit driven by the photon noise limit, which means that in this area, the processing is optimal. And if we look at closer, in fact, it remains an important gain between what we can do at best and the actual performance. And this is especially embarrassing because most of the exoplanet populations are located within this gap. And the issue related to this is the fact that near the star, we are lacking of diversity. The apparent motion of the planet is not sufficient to disambiguate the signature of a planet from the signature of a speckle that share exactly the same spatial shape. This is a blob at the resolution of the PSF. So there is an ambiguity, an interesting ambiguity. So the natural solution is to leverage a database of observation from the same instrument in order to have multiple visualization of the nuisance subject to the same aberration of the instrument, because the aberration is common. And between this observation, we have some strong differences because the star is different, the experience observing conditions are different, and so on. So let's see how it works in practice. So the direct image model is additive, which means that an observed intensity image Y at time t and channel lambda is the sum of the nuisance component F plus the signature of an exoplanet, taking the form of the off-axis PSF, central location xt at time t, and multiplied by an intensity factor alpha, spectrally dependent. And we formalize the detection task or the recovery of the spatio-spectral flux distributions of the object of interest by solving an inverse problem in which the minimized cost function is the sum of two terms. The first one is the data fidelity terms that encode and account for the structure of the nuisance. And it depends on both learnable parameters from the archive of observation, theta in purple, and also from estimated parameters specific to each observation, key of Y, accounting for the fact that we have some specificities in each data. And the regularization terms is here to promote prior knowledge about the exoplanet signatures, and it depends also on learnable parameters new in purple. So we are going to see how these two terms works, and let's start with the first one, the data fidelity one, and its goal is to model the nuisance. And contrary to the first approach I presented, we will not model the nuisance in the pixel space, but in a transform space of features, which means that basically we are extracting collection of patches in the field of view, projecting them with a learnable operator, A, and modeling the resulting sample and not the pixel data by our multivariate Gaussian laws, whose parameters are estimated in the maximum likelihood sense. I forgot to mention that this what I'm presenting here is was developed by a former PhD student who defended last year, Theo Bonrito. We enrich this representation of the data by jointly modeling patches at different spatial resolutions or spatial scales to have more context, for instance, in the sub windows. We do the same extraction, learnable projections, and modeling. We also jointly model pairs of patches diametrically opposed with respect to the star, because we know from the physics of the instrument that we have some kind of symmetries in the nuisance component in this kind of opposite patches. So it will help the unmixing task to have these two samples jointly modeled. So we do the same extraction, projections, and modeling, and we do the same for quadruplet of patches for similar reasons of symmetries. So under this statistical model, the quantity of interest, the spatio-spectral flux distribution of the object of interest is obtained by maximizing the total likelihood that takes the form of a product of distribution, the first product for all times and all wavelengths jointly modeled in our dataset, and second product, this one, the big one, that accounts for the multiple distributions jointly modeled in our problem, accounting for the multiple spatial scales and for the symmetries. And at each point of the field of view, we give a weight to the different distributions, and the weights, W here, are estimated, learned from the data themselves, in fact. So according to the position in the field of view, we give automatically more weights to one of the distributions. So under this model, we can derive the closed form estimators of the quantity of interest, the flux, alpha hat, the associated uncertainty, sigma hat, and the detection criterion gamma. This is the generalized likelihood ratio test that can be threshold at a given value in order to decide in favor of the presence or absence of a planet. And the key point is that these three quantities depends on terms B and A that are here, that involve both the data, Y, the PSF H, and both the learnable and estimated parameters characterizing the nuisance, respectively in purple and orange in the formula. And if we look at closer, this is quite simple. This is just machine filtering. We have in term B, the data Y, centered for the mean, cross-correlated with the pattern that we want to detect, and A, this is just the cross-correlation of the PSF, that is to say, a normalization terms. And behind this cross product, we have the statistics of the nuisance, both learned and estimated. So the sequence of operations involved in term B and A define a learnable module that can be integrated in a neural network architecture. So you have here just a basic illustration with the data as input and the output involving the different steps. Okay, so let's move on to the second term, which is prior knowledge, which is a regularization term, and that enforces prior knowledge about the exoplanet signatures. So the goal is to learn a representation of the exoplanet signatures in the flux maps we obtain under the statistical model, the previous step. So in other words, we want to denoise the flux estimates obtained from the statistical model that I presented just before. And we are performing this task with a small unit that denoise the flux map, and we obtain our final detection map, gamma tilde, and we have also a kind of calibration strategies in order to make sure that we are able to detect planets at a very controlled probability of false alarms, even for very demanding probability of false alarms. I mean, very small probability of false alarms. And for the training, all the parameters of the model of the two stages are learned end-to-end by resorting to the simulation of fake sources into real data. And to do this, we are optimizing the color likelihood, the neglog likelihood. Okay, so here's some results. So, of course, we did several quantitative results and comparing many algorithms. But for the purpose of illustration, I'm showing here only qualitative results in different configurations for different data sets and configuration of the sources in columns. The proposed approach is at the bottom. The statistical method dimension is on the middle. And at the top, you have what I'm calling an oracle. That is to say what we can do as best if we are able to estimate the nuisance parameter without the presence of interest. So this is completely unachievable in practice, but this is just to have a reference. Here, this is the result for good data sets with a lot of data to perform the estimations. And we see that the proposed approach is competitive with the statistical approach and not too far from the oracle. But I will increase now progressively the complexity of the task. And by increasing the complexity of the task, I mean, for instance, reducing the amount of data we have to estimate the nuisance component and to limit the amount of rotation, of available rotation we have of the object of interest. And here we have in a setup with only 2 degrees of rotation, and this is a kind of setup we can have, for instance, on GWST with a very limited role, for instance. And you can see here that in this context, the proposed approach is not too far from the oracle, while a method leveraging a single data set to perform the estimations completely fail and is completely blind to the presence of planets. Now, I would like to illustrate that beyond science data that we're exploring, metadata also matter. And by metadata, I mean, for instance, the monitoring of the observing condition across time at the telescope site. I also mean, for instance, the location in the field of view. This is informative because we saw in the introduction that the nuisance is non-stationary. And I also mean, for instance, the monitoring of the off-axis PSF because it encodes information, for instance, about the quality of the adaptive optics correction or simply to the quality of the observing conditions. And it was the topic of an internship, and the intern proposed, in fact, a strategy to weight the embedding of the science by the embedding of this combined additional metadata information. And the conclusion is that this is informative. It helps the unmixing, especially in the case when we have very heterogeneous observing condition across times, because this mechanism will weight automatically the frames or the position in the field of view impacted by outliers, by bad data. So far, we discussed how to process at inference time a single data set, possibly by leveraging to model the nuisance multiple data sets, but at inference time, we are processing a single data set. And I would like to illustrate now that it's possible to fuse at inference time, multiple datasets in order to improve the detection sensitivity. So this is what we did by fusing multiple observation of the same star, of a given star, but observed at different times across several months or years. And the previous detection task is now recasted as a joint task between detection and estimation of the parameters defining the orbits of the planets span over months or years of observations. And we are obtaining the estimation of the orbital parameters by maximizing a combined detection criterion over the big capital N epochs or number of observations of the same star that are involved. And for doing this, we need to combine the term B and A produced by the previous approach, sampled at the projection of the orbit on the sensor. And we can do this because the term B and A form sufficient statistics in the form that they contain all the information, especially about the uncertainties, to be combined a posteriori. And here you have some kind of results on a system containing 3 exoplanets in the field of view. So the planets are in lines. You have 3 epochs processed independently in columns with a proposed deep learning approach. And here's the result of the combination in a blind fashion, in which we improve significantly the detection confidence and we obtain the orbit of the planets. Okay, so to finish, I have one slide on complementary tasks. So far we discussed how to detect point-like sources, but I mentioned in the introduction that we also want to reconstruct extended features in the circumstellar environment. And here this is just an approach without deep learning. So the data model is the same. The data Y are the sum of the nuisance plus the contribution of the circumstellar environment that we want to reconstruct, transformed by a direct model M, accounting for the instrumental blur, for the apparent rotation, for the transmission of the coronagraph, for the limited field of view and sensor, and for the chromatic scaling of the speckles. We solve an inverse problem. For the data fidelity terms, we account for the nuisance statistics through a separable model to encode for both the spectral and spatial correlations. And for the regularization terms, we enforce sparsity and edge preserving. And the upper parameters, weighting the weights of the different terms, are estimated here in an unsupervised fashion by minimizing a criterion which is a proxy, an estimation of the mean square error in the absence of ground truth. And here you have some kind of reconstruction results we have obtained on multispectral data of the integral field spectrograph of sphere on different stars compared to a method of reference of the field. And you can see that with the proposed approach, we are able to avoid a non-physical artifacts such as discontinuities, and we are also able to improve the spatial resolutions because we are deconvolving the objects because it is accounted for in the direct model. So to go behind, and this is my last slide, to go behind and to improve the statistical model of the nuisance, for instance, leveraging an archive of observation as we did for point-like sources, we now need to shift to a self-supervised approach because we don't have accurate model of the object formation process in the data. We have, of course, hydrodynamical simulations giving a view of the circumstellar environment. They are accurate, but they are specific to each star. And for doing this, and this is what we are currently doing, we are learning a representation of the data of the speckle field, of the nuisance, either by diffusion model or by denoising score model, denoising score matching, in order to learn the distribution of the speckle field or the gradient of the log distribution that can be sampled at inference time in order to explain the nuisance corrupting a given dataset. And you have here some early results. Here, this is some examples of speckles in the database, generated speckles, and here the speckle field is explained on a new dataset at inference time. There is just a timing effect because there is a normalization which is sub-window dependent, I will say. Okay, so to conclude, in high contrast, to process high contrast data, we need to model carefully the nuisance component. And this is the bottleneck because the nuisance component is the dominant component in our data. And to do this, hybrid approaches combining statistical model and deep learning are a powerful avenue. They allow to also perform data fusion by accounting for the uncertainties, and whatever the task, either point lag sources, either detection, estimation, or reconstruction, it's possible to leverage unsupervised algorithms to have our estimates. And of course, in the future, we will be fed by more complex data from the giant project into construction, such as the VLT, or prephase big projects such as the Habitable World Observatories. And by more complex data, I mean, for instance, data with significantly higher spectral resolutions. We have to deal with that, with also a very structured nuisance component, because in all these instruments, the mirror is segmented, not monolithic. And the nuisance will have also some strong instabilities because the instruments are so complex and, of course, more massive. And we are currently preparing the algorithms to be robust to this kind of data. So thank you for your attention.
Thank you, Olivier, for this nice speech. Any questions?
I'm lost in the slides, sorry.
So in the case of the denoising, I've not used denoising, and this is not the first talk where they present denoising. Almost like magic, the noise goes away. So what's the penalty on the data by using a denoising technique? Do you lose at some point some sharpness on the image, or you can push the noise down to like trill the photon noise, or you could get below the photon noise by some magic? No, right?
No, of course not. No, we can't do better than what the theory is scheduling. But yes, in fact, in every method we have a kind of regularization, which means that we have a trade-off between bias and variance, like everywhere. So, for instance, in the object reconstruction task, this is not on the slide, but on the last approach I presented, if we put more weights on the regularizations, of course, we will have well-defined disk on an almost null background. So this is an appealing image, if you want, but we will create some bias by creating some discontinuities. And this is for these reasons that we are trying to balance this trade-off in an unsupervised fashion and to estimate the best weight given to each terms.
So do you have, this is some kind of follow-ups, do you have false positive? Is it possible to have false positive?
Of course, we have false positive, but the fact is that we are controlling the probability of false alarms, because we are providing, the detection criterion can be interpreted in the signal-to-noise ratio of detections, which means that when you are thresholding your detection map at a given threshold, if the model of the nuisance is accurate, you know exactly statistically what amount of false alarm you will have. And this is what we observe in practice. We are controlling the probability of alarm even for demanding false alarm rate. But this is not for at a free cost. We need a calibration step and this.
When you will have the more complex sources, will you be more extended sources?
Mm-hmm.
Because here you're making the hypothesis that it is a point source. So will you be sensitive to calibration effect? To potential
Yeah, this is a good point. In fact, I will say that all systematic sources of error or calibration effects are encoding in the nuisance component. They act as a perturbation of the signal of interest. And
except so your nuisance component can be multiplicative then.
No, this is an additive model. Yeah. That's the point. But You are right, and this is interesting. And in fact, the calibration process can be also be accounted for in the direct model, but it requires more work and to encode precisely the operator involved in the calibration steps. Here, this is not the case. I'm using pre-reduced data, for instance, and learning from this pre-reduced data.
But you do iterate the data, so
Sorry?
you do iterate the data as you show in the beginning.
Yeah.
So this can be solved at this time.